Hi, I'm Mark Woodka, and this is my final project for CS6315. I'm taking a NAND driver framework that was written in C that was developed as a test program for a DARPA project called vSpells that I work on. It consists of a number of good drivers and some with intentional bugs, and plus a framework to test them. I'm attempting to prove the correctness of the drivers, or at least prove certain properties about them that they operate as expected. And also, the intention is to locate some of the intentional bugs that were introduced. So I'm using FramaC, which is a toolkit for analyzing C programs, which includes being able to specify properties and prove whether or not they meet the properties. And the drivers, there are several different classes of drivers. The two I'm working with are named Alpha and Foxtrot. They are the same drivers that I modeled in the P language as also part of the vSpells project. And I'm specifically focusing on properties of the NAND read function, which is where a number of the bugs were introduced. The alpha drivers, they use a jump table to get to their functions, and I don't do anything with the alpha drivers that work with the NAND wait function. That is, alphas 1, 2, and 3. Some of them deal with actual timing issues, and others are just not calling a particular function. But I stuck with NAND read, which is also what I had done in the P model, so that everything I do in FramaC lines up with what I had done with P, just because later on I want to be able to do a comparison of using FramaC versus P. So this is the NAND read function of the alpha 0 driver. So this is the good one, and it's pretty straightforward. C, counting down the length while writing to the buffer and incrementing the buffer. If you go back to the old Unix source code, that you see loops like this all over the place. So starting out, what I do is I annotate the function itself to say what are the behaviors of the function. Like, for example, here it says it requires that the buffer be valid between 0 and length minus 1, so that wherever the buffer points to, that value, that location has to be valid up through length locations total. And then, because the function behaves differently whether or not you provide a correct length, I have to specify different behaviors. So the OK behavior means you gave it a length that's less than or equal to num bytes, which is the page size. And if you give it that, it will assign values to the buffer from 0 to length minus 1, and it'll return 0. If you give it a length value that's greater than num bytes, that's considered an error. It says it assigns nothing, so it doesn't change anything, and it returns minus 1. So then we jump down to the loop. One of the most difficult things with proving programs is that the provers generally can't see into loops. It's like the loop forms a wall that it can't see over, and what you have to do is poke these little holes in the wall with loop invariants to say both to the loop, this are things that should not change through the entire execution. Every time you get to the top of the loop, all these things should be true. And so that is proved within the loop and then seen outside the loop, so that the system sort of knows what went on in the loop. And so I tell it, the length varies between 0 and what it was at the beginning. I say that the buffer starts at what it was at the beginning and can go and gets incremented up through. It's at any one time it's been incremented a certain number of times. And then there's an invariant that says at this point the buffer has been initialized starting at the first position up through however many times we've been through the loop, so that I can show that the loop that's being written in sequential order as opposed to being reversed. And then I had to add these assertions to remind FramaC that the buffer pointer was valid, and I don't know why it needed to know that. And then the other thing was this return length turned out to be a bug. I modified the alpha 0 driver to comment that out, but this was a case where FramaC actually turned up a bug in the supposedly bug-free driver. So let me just show you really quickly. This is what FramaC looks like when everything passes, all these green lights. And this is the alpha 0 driver, the one that's working. And then here's the alpha 6 driver, which you can see all these orange circles are things that it can't prove. And the reason it can't prove it is it turns out it can get stuck in an endless loop if the length is not a multiple of 8. But just to see, one way to sort of show that is if I modify the invariant so that I say the invariant says, hey, if I do expect the buffer to be initialized in reverse order, which is a bug, but if I do that, then it passes. So that tells me that, yeah, it definitely is not doing the buffer in the correct order, because it will pass if I tell it the buffer is being initialized in reverse order. So, in conclusion, using FramaC, I was able to identify all the intentional bugs that were in the alpha 4, 5, and 6 drivers, and also in the Foxtrot 1 and 2. And, as I mentioned, the unintended bug in the alpha 0 where the length was incorrect. The number of lines of annotations I had to add were sometimes double the number of lines of the actual C codes. And it was days and days of trial and error trying to figure out what worked and what didn't. As I say, there's a steep learning curve, and FramaC is not good at indicating what isn't working. So one way, it's a good tool, and one way to start with it might be just to take some little small bit of important code and try annotating that and see if you can prove properties. Thank you.